Welcome to Module 6 for ENVS 254. This is one of the biggest modules of the course, so I might end up breaking this up into 3 videos rather than just 2, but we'll see how quickly we go through it. This will also be reiterated in class, so you don't need to be too stressed, but this is just a good resource to kind of listen on your way to school or while you're at home and you just need something to listen to while you're sitting eating supper or going to bed. I don't know, whatever you like. So this is kind of the pre-processing component of remote sensing. So we're going to look at things such as the platforms, and we're going to look at sensors, and we're going to look at how do you view the data. So there's quite a few components to this particular module. So the learning outcome for the module is to assess remote sensing platforms based on the onboard sensor's characteristics for a specified application in environmental assessment. So we're going to start off with some bare-bone basics, which is looking at resolution. And so objective 6.1 is compare spatial, radiometric, spectral, and temporal resolution. So let's start with spatial resolution. This is one that you guys are mostly familiar with and possibly feel most comfortable with to start with. We're going to look at what does spatial resolution really mean. So if we're looking at a polygon, for example, here, if we have a high spatial resolution, it means we have a very small pixel on the ground, or cell, which is another word for pixel. And so we can really get close to that particular shape of the polygon, because everywhere that polygon touches, it kind of fills in with some of that information. So a smaller cell size is a higher resolution, where as we progress to larger and larger, we start losing the shape of the actual polygon, but it might be telling us some other information. So it's not necessarily that you need to have that exact shape, but it could be giving us some other information. So a larger cell size means that we have a lower spatial resolution. And again, I always suggest do not get hung up on the fact that, 30-meter resolution is bad, because sometimes when we're looking at large areas such as a forest, 30 meters is quite accurate if I really don't care about the individual tree itself and I'm looking for overall patterns. So that is that's spatial resolution. The next one that's listed is radiometric resolution. So this is how many bits does our computer allow. So it tells us how many gray values that we have. Now in class we've talked about digital numbers and what that means. So a digital number goes between 0 and 255 or 1 to 256. Note that this says 256. That means that I can tell 256 different kinds of gray values, or tell between 256 levels of energy and amplitude in order to make my image. As I reduce down in my bit number, I get fewer and fewer gray values. So here you can see it looks a little bit blurrier, but you don't have this weird pixelizing that's happening here, and it smooths it out a little bit nicer in these regions, where this is the 8 level, and then if we look at 4 level, you can really see how much the image has degraded. And this almost looks like something you would see in like a processed medical image, for example. But this is or like kind of like an X-ray, I guess, once it's being kind of pixelized and back projected. But here we have like high levels, we have like a medium level, so we got high, then we got kind of in between, and then we got a medium level, and then we got black. So that's all we can see is those between those, and it's just how sensitive is my sensor. In this case, it's like, did I receive energy or not? That's all it can tell you. So the radiometric resolution here is just how many grays can I see, and how many, if I look at the color cube, this would be two parts, and then 2 parts, and then 2, and all I would have is like 0 to 2, and that's it. Where here I can have 0 to 255. So here's the spectral resolution, and this is how big are our bands and how many bands do we have. So we talked a little bit about bands in our previous class. So we have our electromagnetic spectrum, and we have 3 major types of spectral resolution. So the panchromatic is our first kind of Multi-Spectral Resolution. And the panchromatic means that it's got a long, large, single band that is on the electromagnetic spectrum. Generally goes from about UV to near infrared. So my end result of a panchromatic is it's a black, white, and gray, or also known as a grayscale image. So how it measures this is it uses the total amount of energy across that entire electromagnetic spectrum to be able to create the image. The thing is, it's the lowest spectral resolution, but there is a trade-off, so therefore it has a highest spatial resolution. With multispectral resolution, we have many bands along the electromagnetic spectrum. So here's an example. We have a blue band, which kind of boxed off there, the green band, the red band, and the near infrared. They do not need to be attached. They can be at any point throughout the electromagnetic spectrum. But multispectral means that there's more than 2 bands. So that means that we can actually make a color image with it. So the bands are not large, but they're large-ish, and some of them are smaller or larger. That depends on what spectrum and what your sensor is. And it takes the total amount of energy within that particular band to be able to create an image. And then in this case, I actually get 4 images, 4 grayscale images that show me how much energy it receives in each of those bands. Now, multispectral resolution is the most commonly used resolution. You have that on your phones when you're taking photographs. Our eyes are multispectral. Most of the satellites are multispectral. It's one of the most common. The last kind is hyperspectral. So we talked about hyperspectral in the previous module. And so what hyperspectral resolution is that it is many narrow contiguous bands. So you can see how they're really they're really small compared to these ones, and especially compared to the panchromatic, and they are all attached. So they all connect all the way across. So each of those bands, they're just a little tiny one, and they still take that total amount of energy in that single band to create an image. Each of these create a grayscale image, and then I can put any 3 of them together to create a color image. So it has the lowest spatial resolution because of that trade-off, but it does have the highest spectral resolution. And so it's really ideal for making spectral signatures with your data. The last one is temporal resolution, and this is how long does it take for that to go back and get that image. So here's an example of a weather image every 30 minutes, where this is a city expansion over 50 years. So that is known as a repeat pass. So we can have our orbit, which is much shorter than the repeat pass. Repeat pass means when you come back to that spot, that exact spot again. So it's really important to know the difference between the orbit and the repeat pass or the temporal resolution, where I am actually coming to the same location over and over and over again. So then we can move into Objective 6.2, where we get to compare terrestrial, aerial, and satellite-based platforms in terms of altitude, applications, and resolution. So here's the major platforms. So we have satellite data in the sky, we have high altitude data, which would be an airplane, and then we have low altitude data, which can be like a drone or a helicopter, and then we have ground observations as well, which we can take photos with our camera. So satellite is in space. We can also have deep space probes, which would be like the Hubble telescope. That is also a remote sensing sensor. So because we're going to be dealing more so with satellite orbits in this class, we need to know some of the terms that come with satellite orbits. Whoops, sorry. And so here's some of the names. So we have the ground track along the ground. We have an orbital track. We have a descending, the descending side, or the descending orbit, and then we have an ascending orbit, so it's the direction of which the satellite is moving. We have the equator and an inclination angle, which tells us what angle it is at compared to the equator. Then we have 2 points on the sides, because every orbit is not a perfect circle, it is actually an ellipse. So we have the apogee and the perigee. Sorry, I pronounced that wrong. The apogee and the Perigee. There's a long story behind that. Okay, so the Apogee and the Perigee, these ones are the points at the lowest point and the highest point. And so that's how we define our ascending and descending with the satellite. And one's closer than the other, but I'm not going to expect you guys to remember that for the class, so I'm not going to mention that. But you need to know, be able to label this. We can also talk about how satellites move. So there is geosynchronous and sun-synchronous. So geosynchronous covers the same spot on the Earth all the time. It doesn't move from that particular spot on the Earth's surface. And so generally these satellites are always at the equator. They don't actually see the poles because they might be far out, but they're not actually going to see the very top because it's just going to be too distorted by the time it gets up there. These are weather satellites, and a lot of telecom satellites are like that as well. Then we have sun-synchronous satellites, and these ones stay on the illuminated side of the Earth, which means it stays in the sunlight all the time. They also have another name, which is known as polar orbiting satellites. And so this one's important because it passes the equator at the same time every day, but every time it passes the equator and goes back up, it doesn't mean that it's actually covering the same location on the Earth, because the Earth is spinning underneath it. So the orbit stays the same, but the Earth spins underneath. So that's how it covers the whole entire planet over a certain number of days. So now we can investigate the capabilities and instrumentation of multispectral satellites. So now we're getting into sensors, like what do sensors actually do? So we have three kinds of sensors that we use. The first one is a frame camera, which means I take a photograph of the entire scene all at once. So you're used to that because that's what your cell phone does. That's what your eyes do. We take the entire scene in at the exact same time. Then we have something called an long track scanner, which is known as a push broom scanner. So when you can imagine it looking just like a push broom. So we have a long array at the bottom, and there is like you have your push broom, and you're going to push that broom across in one direction. There is no movement of your body other than your legs that is pushing it in that direction. Now with a push broom, that is what it is doing with a push broom scanner. That's what it's doing as it's collecting data. So it picks up an entire width, swath width is the word that we use, an entire swath width of pixels at a time. So we get a full row of the entire frame, like in a frame camera, we get a full row of that. It has the highest spectral resolution as we collect data. The Crosstrack Scanner is the other one that is used. This one is not quite as common because it requires a mechanical device in it that actually moves the sensor. So this is known as a Whisk broom scanner, or it moves a mirror sometimes, depending on what you're looking at. So the Whisk broom scanner is exactly what it sounds like. So it sweeps back and forth in front of you as it moves forward. So we get one pixel at a time, and they all connect eventually to become a frame, similar like a frame camera. But it takes a little bit longer, and we use these for very particular applications. So if you, like for example, LiDAR uses cross-track scanners for the most part. So some multispectral satellite examples, some have numbers after them because there's many iterations of them now. For example, Landsat 9 is up and running and data is starting to be released to the public. We have QuickBird, we have WorldView, which I think is WorldView 4, 3 now, maybe 5. There's Iconos, Spot, Pleiades, Dove, and so many more. So there's lots and lots of satellites out there. Not all of them are free, some of them are commercial, but depending on what you were looking for and the resolution and this part of the electromagnetic spectrum, that will require you to choose which ones you are interested in. So then we can get into more information about sensors, and that is how do they work? So there is passive sensors and there's active sensors. And so the passive sensors only acquire data. That's it. It's called one-way ranging, and all they do is acquire data. So that means the sunlight is required to be able to give them that information. It is kind of like a camera without a flash. So if it's dark out, the image is going to be dark. Where if we have an active sensor, there's two-way ranging with that. And so that is when you send out energy and you receive energy back. So the active sensors, for example, LiDAR or microwaves, or a camera flash is another one. So it doesn't need to have sunlight. So it produces its own energy. And so therefore we can actually send out different kinds of energy because we can control it. So a term that I've already brought up a few times, just to reiterate here, a band is an area on the electromagnetic spectrum that the sensor can collect. The bandwidth is how wide the band is, or the range of frequencies. So in saying that, those are two terms that you guys are going to see over and over again. We've talked about them lots, and there they are. So going into our next objective is how to acquire an open source multispectral image. So where can we get images? Well, we can go to Earth Explorer, and that's the one we're going to be using in class. There's LandView, there's Copernicus, Sentinel, NASA Earth Data, Remote Pixel, IMPE. There's many more. And depending on, again, what satellite you want to access and how much you want to pay for it, that's all going to be important information to know as well. You can also get images from like the ArcGIS hub. You can also get, because they have an image hub for their image processing package, and you can get data from like satellite facilities like the Alaskan Satellite Facility. So there's lots and lots of places to get data. So what we're going to be using is Landsat data, and it's most of the Landsat data is available on Earth Explorer. So we're going to go to Earth Explorer, and this is how you're going to sign up for an account. So you're going to register, you're going to sign up for an account because we're doing educational use. You can use education. We're not going to be using it for income or anything like that, so you can kind of ignore a lot of that. Just put down whatever option it asks. Then you can set a marker. After you've signed up for the account and you've got it set up, then you can set a marker on the map where you want. So only one point is really needed to be able to access only the points in that location, or only the images in that location. And then we're going to choose a date range. So for you guys, we're not going to choose anything before 2013 because Landsat 8 didn't start up until 2013. So now this has changed again. So what we're going to be using is Landsat Collection 2 Level 1. So we'll be looking for that instead of Collection 1. And so we're going to look at data sets, and you go to Landsat, and I'll be going through this in class as well, so no worries. Then you click Results, and then you're going to find an image with the least amount of cloud or snow. So we're going to see like white or blue fluffy things. And if there's something dark below it, it's a cloud. If it's just like blue, it's usually snow. So blue or white, blue and white is usually snow or ice. So that is, you're going to try to find the least amount. And then you're going to click a download button that looks like a little green arrow with a hard drive. And you're going to choose the largest file to download. So it's likely going to be a GeoTIFF that it'll show up as a data product. So when you download it, you can't open it because it's zipped. So you got to unzip it. So for our class, we're going to unzip using 7-zip. So you're going to extract the .gz file, and then you're going to unzip it in the folder there, and then you have to do the same thing with the .tar file. So you have to unzip this twice. They're big files, so that's why they zip them twice. And then once it's open, once you see that there's TIFF files, now you're ready to start with the software. And we will get going with the software in our next exercise with this. So I'm going to stop the video here before I get into Objective 6.5. And then, because there's a good break time here, then I will bring up the next objective.